Hi everyone, this is a special lecture series for data warehousing and data mining for students who are preparing for end term exams. So for doing last minute revisions, so this is a special lecture prepared for them itself. So these are the following contents that would be covered in this lecture, that is supervised versus unsupervised learning, then classification, which is a two-step process, then decision tree induction, rule-based classification, classification by backpropagation, ego versus lazy learners, case-based reasoning, accuracy of classifier predictor, and cluster analysis. So here we go. The first topic is supervised versus unsupervised learning. So whenever we talk about supervised learning, basically we have a training set that is available with us, and there are fixed class labels. Class labels means there are fixed identifiers that under which identifier a specific item has to be kept on. That is called the supervised classification. And whenever we get the new set of data, that is classified on the basis of training set. So we can see that with the help of an example. Like if we talk about supervised, unsupervised learning. So currently when you had nothing as notes with you or no question papers with you, so you had loads and bundles of books and you are studying from them without knowing that what topic is more important, what has been asked previously in the question papers. So that is called basically unsupervised learning. But the second you get guidance from your faculty that what topics are more important, what topics should be given more emphasis, what are very frequently asked things in your examination. So you get a guidance from your faculty who has a data set from the previous year question papers. So they already know from what unit, what questions are to be asked and what is to be told to students, so they can prepare accordingly. So such type of learning is called supervised learning. So wherein you have the inputs, you have a supervised mechanism, and the data, the training data is already given. So the system has already learned and the respective output is here. So when new set of things come up, then the classifier will check, will categorize whether the data is correct or incorrect. If it is incorrect, then the error rectification will be done, and if it is correct, then the suitable output is resulted in. Like when you as students write attempt a quiz. So in the quiz, whatever answers you are writing in, if let's say it's a multiple choice question and I've made an automated quiz, so when you are attempting, whether if it is a correct answer, then you will get a score for that. If it is incorrect answer, then you will get to know what is the problem, what was the error, what is the correct explanation of it, and you can reattempt it. So you are learning from that. In rest of the cases, like you are writing for, you are attempting an quiz without any answers. So you are just giving input and the system is getting some output. So there is no classification. The system also doesn't know what is correct and what is incorrect. Likewise, you also do not in the first go know what is correct and what is incorrect. So based on similar type of data, then you will start to classify it. So now we have unsupervised learning. The example of unsupervised learning is basically your clustering, and the example of supervised learning is classification. So in unsupervised learning, the class labels are not known. So the unlabeled algorithm is there, which tries to make sense when it gets random data from the test data. So based on that data, groups are made on the basis of similarity index, and then if new data comes up, then if that new data matches any cluster, it will be placed and in that cluster, else it will be a part of another cluster. This is how the unsupervised learning goes on. That means unsupervised learning says it groups and interpret data based on inputs only. So before going with any prediction, it has no classifier, no model that is already made. So based on the data that is available, that is inputted to the system, based on that a mechanism is decided, identifying, let's say, a global optimum solution can be resulted out from the input set. So based on that, the mechanism will be decided on the go, and then suitable outputs will be driven. The special case of unsupervised learning is clustering. Under supervised learning, it's a predictive model or based on the input and output data. So originally the training data is already given to the system, and the system has been trained. So what output should be given on what criteria. So when a new test comes up, a new test data comes up, then it can be easily classified. So the two techniques under supervised learning is classification and regression technique. Now there is another example of unsupervised and supervised learning. So first, let's say supervised learning. Let's say there are different animals that we have to categorize. So what we do is we have to identify whether an animal is a duck or not. If it is a bird, if it is an animal, whatever categories are there, we have to classify whether it is a duck or not. That is the situation at hand. So different birds and animals data sets are provided to the system. So once we start categorizing it, that whether the first figure is a duck or not a duck. So we feed this to the system. If it is a duck, then the system will recognize it. Likewise, for the second case, again we feed that this type of shape belongs to a duck. Then if there is another shape, then we do not say what it is exactly. We tell it that it is not a duck, because our criteria is either it is a duck or it is not a duck. That is our predictive output. So based on that, we have given the feed to the system that whether a particular organism is a duck or not a duck. So initially we have given the training set to the system. We have made the system to learn that on what shapes, what features you have to categorize that whether it is a duck or not a duck. So based on that, a predictive model is decided. Now a new organism comes up, a new test data is given to the system, which is, let's say, unknown data. Now based on the predictive model, that predictive model which is decided from the previous case, based on this predictive model, it will be decided that the features are matching to the training data set, and the features are similar to duck. So now it is a duck. This is a supervised learning and basically the classification algorithm. In unsupervised learning, there is no predictive model. So what we do is we give the input data, whatever different organisms we have at hand. So we give all this input data in one go. Now the system will start to have similarity index. It will try to identify whatever features are based on the whatever features are similar. It will make one cluster. Then this is altogether having different set of features, so another cluster. This is altogether having a different set of features, so another cluster. So rather than giving the output duck or not a duck, it is classifying it randomly on the basis of similarity of the organism or similarity of the item. No previously existing predictive model is working here. So next we will discuss the specific model of supervised learning, that is classification. Now this classification is a two-step process. Since we said it is a supervised learning, that means first we have to make a predictive model. We have to give some training data set to it. We will make the predictive model, and after that we will test it. So the first phase under this is model construction, which says you define the predefined classes and identify the class label attributes, then construct a model using the training data set. So provide the training data set to the system. Once the training data set is given to the system, the predictive model is made. After that, use it on unknown items or unknown objects so that new classification can be checked. Now here, how do we identify the accuracy of the model? Now accuracy basically when we say is the percentage that the test samples are correctly classified, and for that we use the test set, which is independent of the training set. Now whenever we are giving the training set to the system, training set is altogether independent from the test set, so that if both are same, then you will get the same output. You can't identify whether it is classified correctly or not. This is called overfitting. That means if training data set and a test data set are both same, then how can you expect whether the system is giving the accurate output or not, because that data is already provided. So there is no new set of data, so you can't identify whether the classification has been accurately done or not. So it is a better practice to keep both of them separately. Now if the test set is used to select the models, then we call it as validation sets or test sets. Now here's an example for that, for in the two-phase process of classification. So first we will see how we construct a model. Now let's say we have a training data set, and this training data set comprises of name, then rank, then years and tenured. So the rank is, let's say, assistant professor, professor, associate professor, and so on. We have different set of names, we have different years of experience, and whether their tenure is over or not. So next we will provide this data set. We will identify a model, a classifier, a rule on basis of which we are going to categorize this training data. So we are developing a model. The model says if the rank is equal to professor or the years is greater than 6, then tenured should be yes. This is the criteria to segment, to classify the training data set. So this set of data is provided and a suitable classification algorithm is applied, and let's say this is the criteria of that algorithm. So this is how we have trained it. So if we try to match from here, either if it is a professor, then the tenured is yes, or the years of experience is greater than 7, then again the tenured has to be yes. So this is how we have initially trained the data set. Now the time is that we have to check for new entries that whether it is working correctly or not. So for first testing the accuracy of our data set, we have to have a test data set. Before going with the totally unknown values, we are first going to check it before going for the real-time analysis. So now we have kept a separate testing data which is independent of the training data. Now let's start entering the data. If the criteria says if it is a professor, then the tenure should be yes. So first entry is provided to the system. It reads it, neither it is a professor nor the years is greater than 6. So tenured has been put no. Likewise, the next entry comes up wherein the rank is associate professor and the years is 7. So the tenured should have been yes, but here the tenured was no. That means there was a problem when we were training the set. It was not able to classify it properly. The rule was not applied properly. So we will correct these inconsistencies. Once these inconsistencies are taken care of, now we will render the unseen data to the classifier. So now in that unseen data, let's say we have a new entry as Jeff and the category is professor and the years of experience is 4. Now when the system classified, it said tenured is yes. So that means it is correctly classified. So this is how we use classification. The second method is decision tree induction. Now again, the training data sets are class labeled. That means it is again a type of supervised learning. Now in decision tree, it is a flowchart or tree-like structure wherein at the top we have the main criteria, then sub-criteria, then sub-criteria. Now each internal node or a non-leaf node denotes that it is a test on an attribute. Every branch represents an outcome and every terminal node holds a class label. The topmost is the basically root nodes. Now this method of learning is applied till the time the smaller subsets in the trees are built. Now when we are following a decision tree induction, I am taking an example that let's say that A is a splitting attribute where the criteria attribute. Now A can have 3 categories of values. Either A can be a discrete valued, or it can be a continuous valued, or it can be a discrete value and a binary tree. Now let's see this with the help of an example. Now, when I said A is a discrete value, that means at any point of time it can have a unique value. So if A value holds true, then it can have A1, A2 or A3 as an output. For example, let's say we are saying if A is a color, then the color can be green, red, blue, purple, anything. Or if the person has having income, then income can be categorized to either low, medium or high. So this is where when your condition is of discrete value. The second is when your condition is a split value. Split value means there is a range. Let's say the range is, for example, here the range is 42,000. So there would be some output when the income is less than equal to 42,000, and there would be a classification based on when range is greater than 42,000. So we have to take the split points here. So when A is a range, then when A is less than the split point and when A is greater than the split point. The third category is when you have sets in the condition statement. For example, we say that color should belong to either red or green. So output can be binary. It can be 0, 1, it can be yes, no, it can be true, false. So it can be binary. If your condition, if your color belongs to either red or green, then your output will be yes. If your condition does not satisfy color and does not belong to red or green, maybe some other color, then your output would be no. So this is the different partitioning scenarios of your decision tree induction. Now here is an example of decision tree induction. Let's first see at the table towards right hand side. Now here we have age, income, student, credit rating and bias computer. Now we are putting the condition on bias computer. This is the main output that we are looking for. The actual outcome is the output, or the outcome should be bias computer. So if we see the data carefully, then the categories where the categories age are dependent upon whether it is a student or not, and based on that you can identify whether it is going to buy a computer or not. So we are trying to identify the conditions here. So the three conditions are dependent: age, student and bias computer. When we have a split point, that is your age is less than equal to 30 and the student rating is no, then it bias computer. Or if age is less than equal to 30 and your student rating is yes, so it is a student, then it also bias computer. Here if you see, this criteria is not dependent upon income and neither dependent upon criteria. So likewise we will convert it into a decision tree structure. So the main criteria here the first criteria is age. So either the person will be less than equal to 30, or the second category is 31 to 40, or the third category is greater than 40. So if it is less than 31 to 40 and if it is a student, then the bias, whether it will buy a computer or not, no, it will not buy a computer. Again, if it is a student, then it will buy a computer. If age is less than equal to 30 and is a student, then will buy the computer. Let's see the second category, that is when age lies between 31 to 40. Now no other criteria is fulfilling here. Only 31 to 40 and bias computer, they have the direct relationship in between student, income and credit rating. All the three conditions are not required. So you can see from here, if age lies between 31 to 40, then it bias computer. For every condition it holds true. If age is between 31 to 40, it bias computer. So in all the cases it is true. It is not dependent upon rest of the three attributes. So if age lies between 31 to 40, then bias computer is yes. Let's see the third criteria, when age is greater than 40. Here you have dependency upon your credit ratings. So if the credit rating is fair, then what happens? And if the credit rating is excellent, then what happens? So by studying the data, we can see if age is greater than 40 and credit ratings are excellent, it will not buy the computer. So if age is greater than 40 and credit rating is excellent, then it will not buy the computer. Again, this is not dependent upon income and student. So whatsoever criteria is not required, we will not put that in decision tree induction. This is our training data set. Now, based on this decision tree induction, we can have rule-based classification because whatever tree we are making, from the tree we can derive the rules, from the rules we can derive the trees. So, rule-based classification uses if-then rules, wherein, let's say, if R represents a rule and if part represents the rule antecedent or the precondition, that means whatever is the precondition which has to be satisfied. If the condition is satisfied, then what should happen? So this is the rule consequent. For example, if age is equal to youth and student is equal to yes, then bias computer is equal to yes. So if is the rule antecedent or the condition. So if both these conditions satisfy, then bias computer is equal to yes, as bias computer is no. Then how do we assess the rule? That means to what extent the whatever rule we have made has been covered how many branches or how many tuples, and what is the accuracy of our rule-based classification. So for that we have two values, that is n covers number of tuples which are covered by the rule R, and n correct is number of the tuples which are correctly classified by R. So if I have to identify the coverage, so I can have whatever the total number of tuples which have been covered by a rule R divided by the total size of the training data set D. And if I have to calculate the accuracy, what has been correctly classified, so what is correctly classified divided by what number of tuples has been covered by my classifier. Now, rule extraction from a decision tree. Just like I said, you can extract rules from decision tree. From rules you can make a decision tree. So vice versa, both are true. So let's see the conditions that I have written here. If age is equal to young and student is equal to no. So my first criteria here holds age. So if age is equal to young and student is equal to no, then bias computer is no. So I can make a criteria here that age factor, if it is young, if it is middle aged, and let's say if it is old aged. So I have made here three criteria. If age is equal to young and student is equal to no. So next condition is my student, and student is equal to no. Then bias computer is no. Likewise, next condition, let's say if age is equal to young and student is equal to yes. If student is equal to yes, then bias computer is yes. This is how we can make the decision tree. So based on these values that I have written here, I can make a decision tree like this. I have taken the same example that I took for classification, decision tree induction. So it can be easily related, like a rule can be converted into a decision tree and how a decision tree can be converted into a rule. Next topic is classification by backpropagation. Now backpropagation works on the concept of neural networks, the structure of the neuron that we have in our body. So it works on the same concept. So in the neural network that we are using, or I'll say the artificial neural network that we are trying to construct here, has set of inputs and set of outputs. There are some weights associated to it. Then those weights are applied to inputs, they are adjusted, and a suitable prediction is resulted. A suitable output is resulted in. We also call it as connectionist learning, since there are so many connections in between the units. Now there are two methods here. One is a feed forward neural network and second is a backpropagation. Now first let's understand what is a feed forward neural network. Now here we have the input layer. The input layer may be, let's say, the different parameters or attributes on the basis of which you want to classify something. Let's say this is age of a person. Again, I am taking the example of decision tree induction. So let's say it is the age of a person, whether it is a student or not, whether let's say let's see the income level, and let's see the credit ratings. and then we will get the output that whether it will bias computer or not. So this is my final output, bias yes or no. So whether it is a yes or whether it is a no. So I'm taking the same example. So this is the attributes or parameters of my input layer. So this is what I'll give as an input. Then some weights are given to those inputs. Depending upon a pre-worked criteria, there is a hidden layer for taking the input, doing some processing, and that processed data will be given to the output layer. Now there can be one hidden layer, there can be many hidden layers depending upon your complication of the problem, the requirement of your problem. So once this weights are adjusted, then a suitable output is given. For example, I have taken here, let's say the age, whether it is a student or not, what is the income level and what is the credit rating is given to an intermediate node in the hidden layer. It takes some weights, it processes it, and a suitable output is resulted. Now this output will be adjudged here, will be tested, will be classified here whether it gives the correct output or not. So let's say in this case it should have given no, it will not by the computer. So this is a multi-layer feed forward neural network. Now sometimes what happens that whatever is the expected output and whatever is the actual output, they do not match. That means the prediction becomes wrong. But our neural network says you have the inputs, you adjust the weights, you give the weights prior to that and you get the output. Now at this point of time, it's required that first we have to train the system properly. That means we have to go back, we have to readjust the weights and we have to train it in such a way whatever is our expected output and whatever is the actual output, both should match. So for that we use a method that is called backpropagation. We go back, we make some modifications till the time the difference between the actual output and the expected output is minimized to such an extent that the mean squared error between both the actual and the predicted output is minimized. So this is basically your backpropagation. How it works? It says first initialize the weights to a small random numbers associated with biases. The biases are basically your pre-computed constants. So in the first go, initialize weights to all your input values. Then propagate the input in the forward direction by using the activation function. So take the inputs, apply some weights, compute it using the activation function and get an output. Now check for the error. So back propagate the error by updating the weights and the constant value. So see what is the deviation of actual and the targeted value, and minimize those to minimize those error you have to go back, readjust the weights and readjust the bias. This will loop will keep on going till the time the error is very small, very negligible. So there will be your terminating condition. Let's see that with the help of an example. Let's say x0, x1, xn are my inputs which are to be given to my neural network. So this makes my input layer. These are some weights that are given to every input. So x0 is given w0 weight, x1 is given w1 weight, and so on. Then a weighted sum is applied in order to calculate, to do the pre-processing, and a biasness factor, a constant value, is added here. So we will get some output here. Now this output is basically calculated using the function, the weighted approach. That means wi into xi, the summation of all the inputs along with the weights minus your biasness. So this is how your output is calculated. Now this output, that is your actual output, this is matched with your targeted output or your expected output. If there is a big difference, then you will go back, readjust this biasness value, readjust this weights, recompute the activation function, and again obtain an output. Again, if there is a big difference, then you will keep on doing repeating the process till the time your error is reduced. Now once the error is reduced, your prediction is very near to your actual your targeted value, then you will stop. Now your model is ready. Now you can have unknown set of data, you can apply here, so you can get the correct predictions. Now neural network has some weakness and some strengths. Weakness as in it requires a long training time, because first you will give the weights to your inputs, then you will adjust the biasness value, then you will calculate what is the error between the targeted and the actual value, then again you will go back, you will correct, you will readjust the weights, you will readjust the biasness. It takes a long time to train your neural network. Sometimes people are not able to understand the meaning of the hidden units and the weights that are applied. So it's difficult to identify that how the weights have to be arranged, what should be the minimum error that is acceptable. Then there are some tolerances also, strengths also, like high tolerance to noisy data. If the data is noisy or some values are missed, then it can be worked on. This is more suitable when we have continuous value inputs and outputs. Now next topic is lazy versus eager learning. Now lazy learning, just like the name says, lazy. Now till the time you have exams on your head, you will not start learning. So you will only make your schedule when you have exams on your head. Then you will decide, okay, what to learn and how to optimize my 1 week's time so I can appear for my examination. This is lazy learning. On the contrary, there are some students who tend to learn simultaneously. Whether you have exams on your head or not, they know their pattern, that this much schedule they have fixed for daily purposes, and you have to study every day and you have to study this set of data. So when the exam comes up, you know what to revise and how to go about it. That is eager learning. So that was a very lighter version of lazy versus eager learning. So if I have to define it, lazy learning says instance-based learning. Instance means as soon as the problem approaches, you start working on it, then you start to process it, and then you obtain the output. You will not do any pre-computation. You will not compute anything before, you will not make a model before, and you will not go about with the perfect output. So lazy learning says when the problem comes up, then I will start working it. So the system, the training, I'll say the training data set is not processed till the time a query is made to the system. On the contrary, there is another case that is called eager learning, which says whenever the second you give the training data set, it will quickly construct a classification model and it will be prepared for the new set of training data set. So as soon as you give the new queries, it is already ready with its classification, and it will simply match the parameter and give you the correct prediction. Now eager learner requires a lot of time, because when you got the training data set, you have started constructing the model, you are already training your system, then now when the query comes up, you will respond. So you require some more pre-computation time. So you require more time for training because you are going for accurate prediction. On the contrary, lazy learner takes very less time to train the data, because whatever data is available at hand, it will quickly take it, apply what is the most optimum model that should be used, and quickly work on it. But it gives approximated prediction, and it takes more time to predict because a lot of things are to be calculated at that point of time. Now here let's look about the accuracy of our both the learning methods. Now if I talk about lazy method, it uses a very richer hypothesis because it uses many local optimal global solutions or local linear functions, so it can approximate the targeted function. For example, let's talk about Amazon. Now Amazon has new products added almost every day, or let's say on a weekly basis. So whenever you have a new update, you have new items added. So if I am using a eager learning approach, then I will have to have a fixed set of training data set. But my training data set is changing every day. New products are added, new Netflix movies are added, new books are added, let's say on daily basis. So I can't every day train my system. I need to have a constant training data set. So I can't use eager learning here. Here, what is more preferable is lazy learner. The system says, I am sitting idle. Let the data come. As and when you require the prediction, then I will take whatever data is available at hand. I will take it as a training, and I will give you the exact prediction. But if it is an eager learner, it has an obsolete data set because it had a stagnant data set when it had trained the system, and whatever prediction it will get, it will be an incorrect prediction because the data it used is obsolete data. But lazy learner says, I will only compute it when you put a query, when you require a prediction. So at that point of time, whatever data is available at hand, I will take that data, I will quickly train my system, and I'll give you a prediction. Now, in lazy learning method, we have two approaches. First is the k-nearest neighbor approach, and second is case-based reasoning. So let's go about the first technique, that is k-nearest neighbor approach. Now it says all the items correspond to any dimensional spaces, n dimensional spaces. Now how we identify this is we calculate the distance. That is generally the Euclidean distance. So we calculate the distance between the neighbors. So if a new entry has to come up, then we see that to what neighbor it is very nearest to, and we will predict the same output for that. Now let's see that with the help of an example. This is the basic formula for calculating the Euclidean distance. Then we use min-max normalization, so we can bring the value between 0 to 1 range using the functions of min-max normalization. Now let's see lazy learning k nearest neighbor problem with the help of an example. Now let's say the k means the distance, to what distance it has to look about. Let's say this radius distance is basically k is equal to 3. So that is the distance where your problem should look about. Now this green circle is basically a new dot. We have to check that whether it should belong to the category of blue or it should go to the category of red. Now we have the distance as 3. So in this particular radius distance, it will try to identify the neighbors. Whatever neighbor is more closest to the problem at hand, the same output will be given to him. That means it will get the same color of the neighbor which is very close. So if I see k is equal to 3, here there are two red neighbors and they are very close to this new element as compared to this blue box. So here the distance is more, here the distance is very less. So this new element will get the color as red. Now this situation will change if I increase the radius. Now if I increase the radius, let's say this is k is equal to 5. Now here if you have to see that what color it has to be assigned, then I am also counting the I'm taking the basically polling. So whosoever has the maximum count and nearest, that color is given. Like in the previous case when it was k is equal to 3. So red was closest and the count of red was 2. So more the number of neighbors which are having the same property and they are nearer, so they got this green color, got the same shape and same number, the same color. Now if I increase the distance to k is equal to 5, in this case let's start counting the neighbors. When k is equal to 5, that is the outer circle, here this blue color has maximum numbers, the count is 3, and red color has less number. So whatever, depending upon the distance, whatever are the maximum number of neighbors and whatever property they are holding, the same property will be attributed to this new item. So the property of these blue square boxes will be attributed to this new problem at hand. This is how our k nearest neighbor classification works. The second method under instance-based learning or lazy learning is your case-based learning. Now what case-based learning says, rather we have a pre-computed set of cases. We already have some training data set we have given to the system. Now when a new problem comes up, we start look into the database. Whatever is the nearest similar type of database, the same property is given to the new problem at hand. For example, if it is, let's say, a customer service, a product related diagnosis, so you have already, the customer care service has already seen that if a customer has got this problem, then this was the correct solution that was given to him. So if a new customer gets with some problem, it will start to recall that what were the previous categories of problems that it has faced, and if for X problem a particular solution was given. So if the problem matches the X problem, then the same solution will be applied here. This is generally followed in case of, let's say, medical. Now how does your physician works? Now physician has treated a lot of patients, so they keep the history of the patients in a patient database. So whatever cases they have treated, they take the target database, they put it in the in their working memory, that what prescription was given, what type of method was used to take care of this person's disease. So that was captured in the first go. Now when a new patient comes up, that is a targeted patient, so the physician will go and check the patient's record. So whatsoever patient's record matches the new targeted patient, so it will try to identify from the knowledge base history, that means what are the different cases, what methodology was applied for that patient, what prescription was given, what diagnosis was given. So if the case matches, the same solution the physician takes and it is applied to that patient, the new targeted patient. Now how this CBR cycle works. So when you have a new case at hand, you retrieve the previous similar cases. So from that, if you get a case which is similar to that, you will try to adopt the same technique which you adopted for solving the previous problem, similar type of problems. So you will add the case, you will give the same prescription, you solve it, and whatever changes or things you have to incorporate, some new additions you have to do it, then you will revise it, and whatever new changes have been done, you will test it and you will retain that case, and it will be a new learned case. Again, you will save that in your case-based history. So now if a new patient comes up, I will first look into my database. I will match that if the same type of problem has occurred with a previous patient also, then what was the diagnosis, what was the description, what was the prescription that was given. If both the things match up, then maybe I will apply the same set of solution to it, or I will take the same solution plus give some modifications and add on to it and save it as a new case, a learned case, a revised case with me. This is how the case-based reasoning works. Now next is, how do we evaluate the accuracy of a classifier or any type of predictor? So there are three methods for evaluating whether a classifier is giving the correct values, correct outputs or not. So first is holdout method and random sampling. Now what this does is, holdout means in one go we will not take all the data as a training data set. We will take all the data, we will divide it into two categories. First is a training data set and second will be the test data. So not all the data will be given for training. Some data will be held out with the person. So that is why holdout. Holdout means some test data is reserved. Some data is reserved with the person and it is categorized as a test data. Rest of the data is given to our system for training. Generally this proportion is 2/3 of the entire data at hand is taken as the training data set. Rest of the data, that is the 1/3 data, is kept as your test data. Now the training data set is given to the model, so the presets are done, the accuracy is the output is is obtained. So once the entire system is trained, now we have to check the accuracy. So how do we check the accuracy? We cannot have the real-time data before we test for its accuracy. So that is why we have reserved 1/3 of the data as the test data, which is independent data, which is not derived from the previous data. So let's say randomly 2/3 has been kept as the training data and 1/3 has been kept as the test data. Both are independent sets. So once the training is done, once the model is constructed, once the classification is done correctly and you have trained your system, now we have to test whether it is giving the output correctly or not, it is giving the prediction correct or not, or what is the accuracy. So now we use that the reserved test data. So we apply the test data. On that test data, if the system is able to give the prediction correctly or classify the data correctly, then we say the accuracy is good. If there is some errors, then we have to rework with that. So it is basically this method is repeated till the time the accuracies are obtained which we actually expect, which we actually aim at. Now this is a diagrammatic representation of the holdout method. It says first you have the entire training data. So 2/3 entire set of data, 2/3 is treated as your training data set and 1/3 is reserved as your test data set. 2/3 data set, that is the training data set, is used to derive the model and the outputs are given. Now this test set will be applied to the model to check for its accuracy. The second method is basically our cross validation. Now this cross validation says that let's say we categorize the data into some partition the data into some subsets. Let's say those subsets are D1, D2, D3 and so on up till Dk, which are of equal size. That means if one subset comprises of 5 elements, then second subset will also have 5 elements and so on. So how we perform this test set? We say in any iteration, let's say in first iteration, whenever we are performing any iteration, this technique will be performed for the number of folds we have. For the same numbers we will have the same number of iterations. So if I have 10 folds, so I will have 10 iterations. So let's say for first iteration, I will omit the first data set, that means D1, and I will treat the rest from D2 to let's say D10. I will treat the rest of the data set as the training data sets and I will train the model. Then when I have to test the model, I will test it with D1. Next time I will take the values D1 and I will omit D2 in iteration 2. I will take D1, I will omit D2, then I will take from D3 to D10. So for these these data sets will be your training data sets. You will first train the system, then for testing you will use D2 as a data set. So this process will complete, will iterate till the time your all data sets are treated as training data set as well as the same data set has been used as a tested data set, test data set also. Now the third technique is bootstrap. The bootstrap says we will be using sampling without replacement method, which says, let's say if I have a bag of balls which are colored red, blue and black, and if I have to identify the probability which ball is selected, then we have some methods that whether when I pick a ball I count it and whether I put it in the bag or not. If I put that same ball in the bag, then there are chances that next time when I try to pick that ball, the same ball will be captured in my hand and I will count the same number. So that is without replacement. Now there is another method that is called with replacement. That means when I have seen the color, I will put it in the bag. So next time there are chances that the same ball will be picked. So we are using this type of technique for training our data set. what we are doing is we will randomly take one training tuple, and that training tuple will be used as a training data set. Once the system is trained with a training data set, we will put it back into the whole set of data. Again, another training data set is randomly picked up, a tuple is randomly picked up, and the system is trained. Now there might be chances that the previous tuple and the tuple I have again picked up, both are same. There can be a chance that both are different. So this method is called 0.62 bootstrap. The reason being that when we did this type of evaluation, then 63.2 data tuples were there who were identified separately and were used as a training data set. 36.8 the tuples were there or data set were there which could not be tested because there was a repetition amongst the 63.2%. So that is why we call it as 0.632 bootstrap. So whatever data set that is left that has not been trained, that 33.6% will be now treated as the training data, will be treated as a test data set. Again, I am repeating, I have the entire, let's say 100 tuples. So I am using sampling with replacement. That means first I have taken one tuple, I have tested the system, I have trained the system with that tuple, I have put that tuple back into the data set. Again, I will take a tuple randomly and I will train my system. So 63.2% are your independent tuples which were not repeated. So rest which comprises of unique values that were trained, that were used to train the system. Rest 36.8% tuples were left. So though because there was a repetition, so that 36.8% which is left is basically used to test your model. So that is why the name is 0.632 bootstrap. Now if I have to calculate the probability that a tuple is selected, I can use the formula 1 by t. So the probability of not being chosen is 1 minus 1 by t. So when I use this formula that a tuple will not be chosen during the whole time, what is the probability that one tuple will never be chosen? That probability is 1 minus 1 by d raised to the power d. And if this data set is very, very large, then this probability that those tuples which are not selected at all, that probability is 0.368. So that was all with how we identify the accuracy of a classifier. Next is cluster analysis. Now cluster means a collection of data objects. That may be because they are related to each other, or that may be because they are dissimilar. So if they are related to each other, they will fall in the same group. If they are not related to each other, they will be a part of different groups. That is called clustering. Clustering is a type of unsupervised learning where right in the beginning when we are using the data set, we have no predefined classes, no reservations, we will start afresh in that. So for example, this is a basket from which I have to categorize the data. So I have no reservation in my mind that on what criterias, how the data was already treated, how it should be, how the output should look like. So I have no reservations. So randomly we will decide from this basket, like when you go to market, you purchase a set of items, but when you are getting it built, you want to put it in separate bags depending upon whether an element is, let's say, delicate, or an element is eatable, an item is eatable and it's a perishable item, or an item is for household purposes. Let's say I have 3 bags. So I will pick each and every item. Now on the run time, I will decide to what category it belongs to, whether it is a delicate item, it is a perishable item, or it is a household item. Based on that, I will put it in separate bags. So the same method we are using for cluster analysis. Slowly and steadily, you will have all the 3 bags filled with every bag having similar type of items. That is basically a cluster. So considering this example, I have a basket full of different categories of items. Now, if I want that all the items having same color should be put in a separate bag, and so I can carry all the different colored items in different bags. So how can I segregate it? All the green color items, they make one cluster. All the reddish orange color items make similar cluster. Then blue is segregated and gray is segregated. So there is one parameter at runtime. The parameter was color. Maybe second time you want to categorize it by shape. So whatever is near in approximately of the same shape are to be put in the same box. So these two are approximately of the same shape. They are put in the same box. These are approximately oval or circular in shape. Again put in the same box. Maybe the next cluster criteria may be size. So whatsoever is big in size is put separately. Maybe you can give the what dimension of that size, that if the size is greater than this, then it has to be put in a separate box. If the size is less than this, then it has to be put in separate box. Likewise, you can decide on runtime that what should be the criteria for making different groups. Now we should admire that whatever groups here are made depending upon any criteria, that have one thing in common, that elements belonging to one group have almost same properties. Elements belonging to this group have same property, that means the color was same. So the similarity index has to be high. If there is a big difference in the similarity index, the color of this and this both are different, then they have to be put in different groups. So if they are dissimilar in nature, they will be segregated. They would be segregated in different groups or different clusters. If they have similar set of parameters, they would be put in same group. Now there are different applications of clustering. Like if I have to categorize a new bird I saw flying, so if I have to categorize that bird, I will identify that to what species it belongs to, what genus it belongs to. So based on some parameters I will categorize it, and when I will call it as this particular type of bird. If I see some organisms which are very small in nature and which can fly, I will call them as insects. So based on the similar characteristics, we can cluster. So we can use clustering in biology, in information retrieval. So similar type of documents can be clustered together. In let's say when you are doing marketing, then you have to identify the similar customer bases. For example, for a particular telephone subscription, if they want to give some discounts or coupons to higher profile customers, they will identify who are the people who are using high plans of calling and belong to have what type of income level, and some XYZ schemes can be given to that, and similar type of promotion will be given. So if you see that when you are using some telephone subscriptions, then if you are using a 299 plan, you will never have an option to degrade your plan to 199. You will always have an option to upgrade it. If a person is using 199 plan, he will get the options of only 299. If a person is using the telephone plan of 500 and above, he will only get the probable set of new packs which are of higher range. So this is how they are targeting the customer base for marketing purposes. Likewise, for city planning, let's say if a new site has to be developed and different categories of houses are to be put in, then what is the value of that place, then what is the size or what is the area of that place. So based on that, we have to make LIG flats or MIG flats, or at which locations they should be placed. So for this type of planning also, this clustering is applied. Likewise, there are many examples where clustering can be applied. Now while we are doing cluster analysis, there are two categories of data. First category is the data matrix. That means when we are discussing object by variable structure, which means I have two set of attributes which I am comparing. For example, I am comparing person and income, person and age, age and income. So I am taking one object and one variable. So person, age, person, income. So I am taking object, n object, that means n persons, and p variables means different income age groups, different age groups. So I will have first entry as P1A1, second entry as P2A2, and third entry, and so on, the respective values. If I have this type of matrix, then I will call it as a data matrix, wherein I am using object by variable structure. The second matrix is object by object structure, or I can call it as a dissimilarity matrix. That means when I am comparing one object with another object. For example, I am comparing person with a person. So internal attributes I am considering. I am considering an employee of the organization with respect to a superior person in the organization. Both are employees. So a subordinate versus a let's say superior person. So both belong to the category employee. So my matrix is employee versus employee. So employee into employee structure when I make, this is called a dissimilarity matrix. Now, what is the criteria for good clustering? Every cluster which has high intra-class similarity. That means if this is one set of cluster wherein there are some items placed here, and there is another set of cluster wherein we have another set of items. So the good clustering is when the items within a cluster have more similar features than the items in another cluster. So if I have to compare this square with a circle, there are more number of differences, more dissimilar features, more dissimilar parameters. But when I compare these elements within the group, the similarity is high. So we need to have intra-class similarity as high and inter-class similarity as low. So this, if we have the strong bonding, this is called cohesiveness. If we have more dissimilarity between different types of cluster, we call it as distinctive between the clusters. So the quality of clustering depends upon the similarity measure, how we implement it, and how much hidden patterns we can discover, or how much new knowledge we can identify from these clusters. Now, there are different clustering methods that are that are widely used. First is partitioning approach, then hierarchical approach, density based approach, grid based approach. So let's see every method one by one. First is a partitioning approach, which is using basically the k-means clustering method. Now this says it is implemented in 4 steps. The first step is that you should have k non-empty subsets. Then whatever the number of subsets are, you have to identify a centroid of each subset. Centroid means a mean point of the cluster. That mean point is you will have all the elements in the cluster. You will take the mean of the cluster, and wherever the mean is located, that will be your centroid. Now you will start identifying the distance of the centroid and the different items that are placed in your cluster. So whatsoever are nearly located will be the part of that cluster. Whatever is far from that centroid will be removed from that cluster. So then it will become a part of another cluster. This shifting in shape will keep on changing till the time there is no more changes in number of items within a cluster. That means till the time we have higher similarity index and lower dissimilarity between within a group. Now let's take that with the help of an example. Here k refers to the number of clusters. So you have to have an assumption that how many numbers you want to make. You have to have this prior in your mind, that what are the number of clusters you are currently looking at the current time. So let's say I only want 3 clusters. So this is the number of items that are placed. Now arbitrarily we will partition into some random number of groups. The first partition, the first clustering will be a random clustering. Now within that clustering we will locate, based on the items that are here, we will locate what is the centroid of that cluster. That means what is the mean point, what is the mean of all these points. We will calculate the mean point and we will mark one object as the mean point. Next we will identify the distance from this centroid to other items. Now whichever item is far from one centroid, then we will isolate it from the current cluster, and simultaneously we are working in other groups also. So we are mapping distances from other centroids in the cluster to other items. So whatsoever item is near, we will keep it as a part of one group. Whatever is far, that will become the part of another group. Now once this rearranging is done, next again our mean is going to change, because when the number of items and the value of items changes, your mean value again changes. So now if you see this diagram, this outer layer was the original partition. Now when the the clustering is changed, the distance was calculated, then the new size of the cluster became this. That means some elements which looked pretty far from the existing centroid are removed from that cluster, but on the other hand it became part of another cluster. So if you see, it has become a part of a new cluster here. These are the new clusters. So whatever, and again the other outer cluster size has increased. So this rearrangement is done. Again a new centroid is calculated. Again the distance of centroid to all the items is calculated. So if it lies between the range, then it will be a part of this cluster. Else again there will be a shift in the number of items from one cluster to another till the time there are no more rearrangements. So this is the final cluster size that we have got with the final number of elements, and this is the, let's say this is the final location of your centroid. Now if I again run the iteration and again calculate the mean point and start calculating the distance, it remains fixed. There are no more changes that are happening between the different types of clusters. So this will be my termination condition. This is called k-means clustering. So I am calculating mean of every cluster, and the size, the number of the clusters are fixed here. There are some problems with k-means method. Now if there are outliers, that means if I go to previous case, if there are outliers means some element located pretty far from here, then because of this outlier, if I try to calculate the mean, here the mean value and here the mean value, there will be a drastic change in the values because of one outlier. So if I have to calculate, use this outlier, my maybe the cluster size, maybe the number of elements will be distorted. So for that, rather than using k-means, we try to use the next method, that is medoid. So how we calculate medoid is basically by looking at the set of items. We try to obtain the most centrally located item on random basis in the first go. So first go randomly, we will identify the most centrally located item. Then again we will start calculating the distance. In the previous case we were taking mean. So if an item is located very far, so the distance value is more and your mean value will drastically shift towards some other side. In order to take care of that problem, we are using medoids. So how this medoids work? Let's say this was my original data set and my k value, that means the number of clusters has to be 2. So depending upon the location of my clusters, we randomly identified two items as medoid. So one is this medoid for this particular cluster. One item, this is treated as a medoid, which is the most centrally located point for this particular cluster. Now the distance is calculated and again we will identify the most centrally located item. So maybe it can change and it may not be changed. Now when we are changing the centroid to some other item, we are identifying that if the new item that we have just taken as a centroid and the previous item, if there is a big change in the cost, big change in the optimization, then we are going to, if it is minimizing my cost function, then we will swap these points and we will have a new medoid. If the cost is not decreasing, rather maybe it is increasing, then we will keep the original values. So let's say in this iteration, this was my medoid, this was my medoid. Now here I have located one more value for this particular cluster, identified that this is more centrally located value. Now I will have to compare the cost when I treat this value as the medoid and when I treat this value as the medoid. If I treat this as the most centrally located item, then what is the overall cost of my performing this model, performing this prediction or giving outputs? So what is the cost of my system that time? If the cost decreases, then I will treat this value as my new medoid or new most centrally located item. If it is increasing the cost, then I will remain with the existing previous medoid. So this is how our k-medoid works. We also call it as partitioning around k-medoids. That's also called a PAM. So this refunctioning, reallocation of items and identifying of the centroids, this work is done till the time the cost becomes stable. So there is no more better changes in the cost. Till that time, this iteration will keep on going. Once we obtain a suitable cost, a suitable optimum solution, then we will stop here. The next method under clustering is hierarchical clustering. Now here we are talking about nested clustering. That means one cluster within a cluster within a cluster. For example, at the top, if I look at the geographical conditions, then let's say India is a big cluster comprising of all the states. When I peep into India, I have different zones: North India, East India, West India and South India. So there are 4 clusters. So if you see the attributes of people living in North India, they are quite similar. You can identify easily this person is North Indian, this person belongs to Eastern states, this person belongs to the Western states, this person belongs to the Southern states. So you can easily identify those clusters. Again, if I have to go down to North India, then I will, let's say, go into different states, and again there will be some similarities between different states. You can easily identify this person belongs to Jammu and Kashmir, this person looks like he belongs to Punjab, this person looks like he belongs to Delhi, based on some similar attributes, maybe their language, maybe their dressing style, maybe their appearances, so maybe their culture. So based on those features, those parameters, you can decide different clusters within clusters. So when you go up, you will have broad range of parameters. When you go down in the cluster, you will have specialized features of the cluster. And at any point of time, I can divide the entire cluster and I can get a segment of it. That means if I want to just compare people of Delhi with people of Punjab, so there are 2 clusters from North India, I can divide the entire country. I will take the segment of North India, I will cut the segment into 2 parts of Delhi and of Punjab, and I can do the comparison. So whatsoever clustering you want, you can obtain it. This is called hierarchical cluster. At the top you have the master cluster, then inside you have subdivision, then you subdivisions, and there are segregated cluster. We see this hierarchical cluster in the form of a tree-like diagram, which is called dendrogram. So the outer one is the master cluster, then 2 clusters in between. This space is the overlapping space between 2 clusters. Some similarity between people of Punjab and people of Haryana. Those similarity you will find in Chandigarh or Ambala. So this is some similarity. A mixing of clusters is always possible. So that is called a hierarchical cluster. If I want to divide, check one clustering segment, I can divide it from here. I will have some attributes of this cluster as well as this cluster. This is your hierarchical cluster. Now, when we are using hierarchical clustering, then there is no assumptions on how many number of clusters should be there. Like in case of partitioning, we were using the k value that we have to assume, we have to decide previously before applying this method that what should be the number of clustering. It is very simple to get as many desired clusters as possible. Just cut the dendrogram at the proper level and you can get the number of different clustering. Generally, we use this in biological sciences. Like if I have to categorize a bird, then it belongs to this phylum, it belongs to this class, it belongs to this genus, it belongs to this species. So generally, we use it for biological sequences. Now, this hierarchical clustering is further divided into two. That means based on whether you are first taking a big cluster, then subdivided into smaller clusters, or you are first taking smaller clusters and then combining to form the bigger clusters. So based on that, we have the names bottom-up approach or agglomerative approach and top-down approach or divisive approach. So agglomerative says first we will have a smaller group of cluster. Then we will see whatever are the nearby clusters which has similar property, join them, keep on joining till the time you reach to a higher cluster. The divisive property says you first take the biggest cluster, India, then you divide it into zones, then you divide it into states, then you divide it into further, let's say, cities. So this is a top-down approach till the time you reach to the final splitting, that now let's say Delhi cannot be split anymore. Then Delhi is the final splitting. So whatever are the characteristics of the Delhi, that will be common in all the areas of Delhi. That's an example. So this can be done, this splitting will be done till the time you think now no more splitting can be useful for us. So with the help of this diagram we can see here, then agglomerative says initially we have small set of clusters, we combine to form a bigger one, then ultimately we get the biggest cluster, that is agglomerative approach. So the technique here, the model here that is used is Agnes. The second is a divisive approach which says first we will have the biggest cluster, then we will divide on the basis of it. So we will have one cluster which is more similar here, another cluster, then again this cluster is broken down further, this cluster is broken down further till the time you think now these clusters cannot be broken down in next go. So this is divisive approach, a very known approach that is used under for this hierarchical cluster in the divisive technique is Diana approach. Now next technique is density based clustering, which says the entire clustering method will be based on density. For example, if we had to locate the hotspots in India when COVID started increasing, the level of COVID started increasing, or even nowadays when the level is increasing. So if I have to locate the what are the more prone area, or what areas have to be put in quarantine. So wherever there was higher density and there were some cases that area was kept as a quarantine zone or a restrictive zone. Wherever the density of people, the density of population was less and the number of cases reported was less, that was not treated as hotspots. So based on the density, the clustering is done. So this is one example wherein this density based clustering was applied. Now next is grid based clustering. Now grid based clustering says all the objects it use, they form a grid wherein the members in the grid, these represents cell, these are the cells in the grid. So together it forms a grid structure. Now here the entire let's assume something that let's say we have the set of records and we want to cluster all the records with respect to two attributes. Maybe let's say the number of people living in a particular area and the number of wildlife animals that are available. So two criterias, we want to divide it so that we can show in the form of grids. So there are some examples. Let's say the number of road signs per kilometer, so we can make it on the grid depending upon the density of the people living and the number of road signs. Likewise, the number of tigers in a particular square kilometer. Like this method is generally used when we want very fast processing, and the number of cells can be easily quantized. The attributes can be easily quantized, and we require multi-resolution. That means at different levels of summarization and different levels of details, we want to analyze the data. There are some other techniques that are here, that are model-based techniques, wherein we identify different models for each clusters. We test that when if one model is suitable for one cluster, then we try to apply the same model to other clusters. So whatever is the best fit model, we can utilize it for clustering method. There are different methods under that which are written here. Next is frequent pattern based clustering. That means on the basis of what set of patterns are existing together, based on that we will categorize it. For example, in Big Bazaar, you will find that some section has imported items that are kept on shelf, and some places you have local items that are kept on the shelves. So based on the purchasing power of the people and the type of people that visit that store and visit that particular section and what they tend to buy together, this planning arrangement of that store can be done. This is basically frequent pattern based. Then next is constraint based or user guided. That means your clustering will be done on the basis of the constraint that are applied by the user. For example, when you look into 100acres.com, then you put some criteria, you put some constraints that I am looking for 2 BHK apartment with let's say rental of at least 30,000, so it should be a posh apartment, and the nearby connectivity to airport should be there. So you are giving different constraints. Based on those constraints, you will get the set of properties. This is called your user guided or constraint based clustering. Last is your link based clustering, which says that all the objects are linked in such a way that, for example, I have made a diagram here that there are different clusters, and item of one cluster in a way is connected to one or more items of the second cluster. So this is basically the link based clustering, that two clusters are connected with one item which may have common property of both the clusters, and it has some link with other clusters. So this is basically a link based clustering. So that's all with the revision for your data warehousing, data mining. I wish you all the very best. Do good in your examinations.